megahertz, and this is at a redshift of the Z equal to 0.034, and these are the RA tag of the source. It's in the constellation of Hercules, and to get the data, we have used this instrument called nuclear spectroscopic telescope and Rooster, and which is a space-based X-ray telescope, and it is to study the emission in the range from 3 to 79 keV, and it has two focal plane modules, FTM and FTME, and this is the diagram showing the Rooster configuration is stored in deploy mode. Next is the Swift XRT to study the soft X-ray part of this emission, which is from 0.2 to 10 keV. And also we have used this multi-wavelength study. So for that we are also interested in studying the UV part, and which has 6 filters, 3 in the optical and 3 in the UV. That is the BBU, and in UV that is W1, W2 and M2. And the detection range of UVOT is from 170 to 600 nanometers. So these are the observations that we have considered for the to carry out our work, and these are below. This is the Swift XRT concern. I'll come to that why it's important. And the data analysis for Rooster, we have used the standard procedure, a new pipeline which is integrated in HESOFT, and we have extracted the source region and the background region in DS9. And there are files called Pearl site analysis, the response file, which is the response of the telescope, and these files we have created using the two new products, and these are finally grouped, and we have obtained finally the group PHA file, which can be plotted expect. And for Swift XRT also, this is the same procedure. However, the Swift XRT, as I've already shown the Swift counts, sometimes the Swift XRT faces a bit of pile-up issue. The pile-up means that there are at a specific instant there can be multiple detection of photons, and to remove it we do some standard procedure of selecting inner region of inner radius some value and the outer radius, and we try to remove the pile-up from the source, which is mostly accumulated in nearby the source region. And for UVOT also we have taken the we have considered this galactic extension by reddening, and we have found out the flux and the energy of the filters, and we have also we could get the data for 3 filters in UV, but I mean not in optical. And so coming to the spectral analysis, so basically we have considered a spherical region of radius earth, and it is filled with some tangled magnetic field. Then we have considered some isotropic electron distribution given by this Lorentz spectrum, and below is this equation 1, which is the synchronous flux, and this was solved numerically, and it will as a local model in expect, and where we have given this particle distribution function, and to account for the galactic absorption we have used this model called TBEPS, which is given by where the NH value is given by this factor. And here is the equation, which is the dl. Here is the luminosity distance with the volume of the emission region is dependent on this electron charge magnetic field, then the mass of the electron, speed of light, and this is a factor which is used to which is the root over c, that is dependent on some Doppler shift, magnetic field, and the shift. So next is the model that we have used, the particle distribution model. Basically what we do is that we have considered some Laconic model, Laconic scenario, so where we take some electrons and we put some interaction so that it can emit the photons in a high energy. So this is a particle distribution given by this equation 2, where alpha is the particle index, particle spectral index, beta is the curvature parameter, and k is the normalization of the particle density. And this is a transformation that we use to that we have used here. There is chi is related to Lorentz factor times root over c, and c is related to this factor by this Doppler shift and b and the red shift. So these are some of the base fit parameters for the block parabola model. So next is the particle distribution with a maximum energy. So where we consider some escape time scale of the particles, like when a particle interacts with the shock front, and the particle will be accelerated to very high energy, and the escape time scale of going out from the particular region. So we have considered, and for this, and also there will be some cooling, as this will emit the radiation, and we have considered this synchrotron cooling term. And here is the relation, like T is dependent on, directly dependent on tau, the acceleration time scale, and the Kinex is related to this, as I've already mentioned, and this Lorentz factor max is inversely proportional to the acceleration time scale. And these are some of the base fit parameters that we could obtain. Then next is this energy dependent diffusion model, where the escape time scale of the particles are thought to be energy dependent. And this is the particle, the equation 6 gives us the particle distribution, and this is a factor psi, which is given by this relation. And yeah, so this is the base fit parameters again for the 6th observation. Then next is the acceleration model, that is the energy dependent acceleration, where the acceleration of the particles are dependent on this energy, and we have considered for this case also. So next are some of the preliminary results that I wanted to show, and these are the spectrums that we could obtain. So first is this black lines, which are the UVOT observation, then red is the swift XRT, then blue and green defines the two focal plane modules of Newstar. So first one is the spectrum for log parabola. This is for the maximum energy model. Then this is the energy diffusion model, and this is the this is the energy dependent acceleration, and this is the energy dependent diffusion model. And these are some of the correlation plots, okay, so before going to the correlation plots, this is one of the observation where we can see some peculiar behavior with swift XRT, because it was showing some upward trend which was not seen in the other observation. And earlier we thought of that it might be due to some pile-up region, but we checked and we didn't find anything. But we are still unaware of why we are getting this. And these are some of the correlation plots where we can see a bit anti-correlation between 2-3 observations, but not very prominent. And also this is a correlation plot between the spectral index and the curvature parameter. And this is for the similar case for the EDA model also. So finally, the conclusion, all the observation S1, the observation dated this seems to be well fitted with all the models. Then for this swift XRT spectrum in S5, there is one observation, as I have already shown. Seems to follow some upward trend, which is also free from pile-up, and there are anti-correlation of some parameters. So in future work, this is we think that we need to also get some data in gamma band from the observation, the instrument like Lab. See how the spectrum gets fitted with the convolution model, so that we can give some more insight to this similar of laser. So these are the advances. Thank you so much.
Thank you, Ritik, for nice and interesting presentation. It's now open for discussion. See, any question?
I have one question. If you go to slide number 17,
Yes.
so your gamma max is the Lorentz factor, right?
Yes.
And what is beta is?
So beta is a cooling term.
So
Like,
the Lorentz factor is a quantity
Yes.
which exactly depends on the velocity. Then how it should depend on cooling factor?
Actually, sir, the cooling term basically defines that whenever the particle is the electron population undergoes a synchrotron evolution, then this is the synchrotron cooling that has been considered for this.
That I understood, but I have some reservation because the Lorentz factor is a property which
Yes,
is
that is
mainly dictated by velocity. Then I see you are connecting it with the cooling factor.
Yes.
I'm a little bit confused here on how cooling can control Lorentz factor.
Actually, sir, this is like, okay, but this is a transformation that has been used basically, like Kinex, then from this we have got this value Like this is the value of C where the magnetic field and dependence on the Doppler shift, basically this C, it depends on the Doppler shift and this value of B and the red shift. And from this transformation we can get this, we have considered this inversely proportional to the acceleration times scale. Like and when the particle will be accelerated, there will be an inversion in the